So, good afternoon. I'm Dr. Kanade. We will start with our today's lecture, which is a continuation of our yesterday's lecture, where we started discussing about the instruction set of PIC18F458 microcontroller. Okay. In yesterday's lecture, we have seen the programming model of the PIC18F458, and we discussed that there are 77 instructions, out of which only 4 instructions are 32-bit and rest 73 instructions are 16-bit instructions. These instructions are grouped into 4 categories: byte oriented, bit oriented, literal, and control. Out of these, we have seen byte oriented and bit oriented instructions yesterday. Okay, and today we will see these literal operations and control operations, and we will also try to cover some of the arithmetic instructions today. Okay, so I will skip to the literal operations now. So the word literal means the value. Okay, so when we say that the literal operations, it means that that instruction is going to operate on a particular value, means a particular data value. Okay, it is not going to operate on an address, it is going to operate on a value. And in general, this literal is mostly specified by k. Okay, in while writing a instruction in syntax form. Okay, whenever in a syntax we see k, it means that it is a literal. Similarly, yesterday we have seen f being written in the instruction. It means that the instruction is operating on a file register address. Okay, these kind of instructions will at least most of the times will have a literal value which will need to be loaded in a file register. Okay, sometimes it will also have the number of the FSR. FSR is file select register. We have seen this FSR here. See, here we have this FSR. What is this? This is a file select register. It is a 12-bit register, right? Means it holds 12-bit address of the data memory. The full address of the data memory it can hold. Okay, so and in the PIC18F458 we have 0, 1, 2, means 3 FSRs we have. Okay, so in some of the instructions we can also have the desired FSR, which where we want to load the literal value. Okay, some of the literal instructions may not even have any operand. Okay, of course we are going to see examples and we are going to use all these types of instructions later on in our programs. Okay, the structure of this kind of instruction is like this. The literal in general is 8-bit. Okay, 8-bit value, and then rest of the 8 bits are opcode. Okay, for example, the most common type of instruction that we are going to use in from this category is like this: move LW. Okay, what it indicates, whenever in a instruction there is this letter L in a instruction, I'm saying, okay, in an instruction whenever there is a letter L, it generally indicates literal. Okay, and what it is going to do is move L to W, means move a literal value to W. W is working register. Okay, so and in this instruction what we have to specify the literal value, right? We have to specify this k in the instruction. So what this instruction will do, it will load or copy or move this value 0x5a, means 5a hexadecimal number, to WREG. Okay, WREG means working register. Now you might have noticed the sequence of the operands. If you remember in 8051, there was also an instruction move, MOV, and there were parameters. For example, move A, B. But in that case, the sequence was move destination comma source. It was like that in 8051. So when it says in 8051, when it had move A comma B, okay, when we had this instruction move A comma B, what was happening was the value of B was getting loaded into A. Okay, this was in case of 8051. However, in PIC18F, the sequence is straightforward. First, the source is always given, and then the destination is always given. Okay, so this instruction, remember, move LW is going to copy the contents L to W. Now remember what I'm saying, contents directly, that is a value. It is not a F, it is not the register, right? This is not the address of any register. Okay, this is the actual value that is going to be copied, because there will be some other instruction where move FW, for example, where value inside the F register will be copied to W. We will see that afterwards, because it is not part of the literal instructions. Okay, so the fourth group of instructions is now the control instructions, which are actually used to, in general, transfer the control of program execution from standard sequence to other sequence. Like, see, as any program, we write instructions from 1, 2, 3, 4, whatever the number of instructions are, and those instructions are executed sequentially from top to bottom. Okay, like in any programming language. However, if we want to change this sequence in some way, for example, you know, a loop, you have used some kind of looping instructions, for example, jump. So let's say after this instruction I want to go back to again here, let's say 4 times. So what we do, so what it means is we have to transfer the control from, instead of going to the next instruction, we have to go back to the second instruction, for example. So we are transferring the program execution control. So these kind of things happen in the control instructions things. Okay, so in general, the operands in this case are the program memory addresses. Okay, program memory addresses. Why program memory? Because these addresses are the program memory addresses. Instructions are stored in program memory. So what we will tell the program, that instead of going to the next instruction, go back to the previous instructions. This is how we are going to change the program flow. Sometimes we may also do after executing this instruction, go here, and once you complete the task, then you come back here. This kind of also work we do. What is this called? This is called subroutines. Okay, so we can also use subroutines where we have to transfer our program control, and that is one of the instructions to do that is call. You have seen this instruction already in 8051 also. So this call instruction also will change the sequence of execution. Once we start here, and let's say here it is call, okay, and from here the execution will go to this section, it will complete that section and then come back to the next section after the call. Okay, so this can also be one of the this can also be the instruction, and if this is the instruction, then there is a mode specified by the specified by letter S in the call instruction. We will see in details afterwards. Okay, then the mode of the table read and table write instructions can also be given for the control instruction. These are also separate type of instructions, and we will see. There can also be no operand at all given to the instruction. Some instructions are like that there will be no operand. For example, return instruction will have no operand. Okay, examples, here only we are talking about the names of the instructions. We are not actually looking into details of these instructions. Okay, one of the very good instruction you can say is go to. It's as the name says, go to will take the control from one location to whatever location you want. Go to label. So label can be any, we can give label to any instruction, and basically it will be a, when it the program disassembles assembles into assembly language, here will be a address, and that will be 20-bit address. Okay, it will be a 20-bit address of the program memory. Okay, so what it means is, if we use go to instruction, we can jump to any location in on the program memory space. If this is the program memory, okay, if this is program memory, it starts from 0 to how much? To M. We have 0 to 2M possible locations. So this go to instruction can have any address from this, and it can jump from any location to any location without any restriction. Okay, that only restriction will be whether that memory is available to us or not, because some part of memory is not available in the PIC18F458 IC. How much memory we have here? Only up to 7FFF is available. If we try to go here, we only will get 00. Okay, but the point is, go to instruction can take you to any location in the program memory. Okay, this is called long go to or standard go to. Okay, a very similar to this go to instruction is the BRA. BRA stands for branch. Okay, so what it does is, branch, it will simply take the control of the program from one location to another. However, the jump, the extent of the jump is limited. Okay, the extent of the jump is limited by 11 bits. Here you can see 0 to 10. Okay, so 11-bit value is available here, so it can jump only, it is called a small branch, small jump or small branch instruction. Okay, exact details about this we will see later. The difference here you can see, this go to instruction is how many bits? 0 to 15 plus 0 to 15 is equal to 32-bit instruction. Okay, go to instruction is a 32-bit instruction, whereas branch instruction is 16-bit instruction. Okay, so this is the difference, that using branch instruction we can save a program memory space, 2 bytes of program memory space, because when you grow your programs, you will also have to take care that the program memory is utilized very preciously, because program memory is limited to us and we cannot waste the program memory if it is not required. We will see the exact differences between go to and branch when we actually talk about this instruction in second unit. Okay, similar to this 32-bit instruction go to, the call is also a 32-bit instruction. Call instruction works in this way, as I said earlier. Okay, this call instruction is also 32-bit. This will also take the control to anywhere in the program memory location. However, the difference between go to and call is, after the call is used to call a subroutine, and you can return back to the next instruction after call by using a return instruction, whereas that facility is not available in go to. Okay, how this is going to work exactly? It is going to be taken care of by the stack and stack pointer. Now I am using many words which you may remember from 8051, or you may not remember from 8051. Anyway, don't worry. In this section we are only taking an introduction about the instructions. and we are going to see all of these instructions in very detail along with example, because you have to use these instructions for implementing some of your programs. Okay. Then there are kind of instructions which are called branch along with a letter. Now this, what it says is branch if carry, branch if not carry, branch if 0, branch if not 0. What are these 0, carry? What I'm saying, these are the status bits or the status flags. Okay. Okay, so these branch instructions are also part of the control instruction types. Okay. Okay, so now moving on, we will now jump to the actual detailed descriptions of the instructions, and to begin with, we will start with the arithmetic instructions. Okay. The first instruction that we are now seeing is add LW. Okay. Now, what it indicates, as I said, this L in the instruction stands for literal. Okay. L means literal. So what this instruction is going to do is, it is going to add the literal provided in the instruction to the contents of working register W, and the result will be stored in W. So this is the operation W. These brackets around W indicate that it is the value inside the register. It is the value inside this W register. That value plus K, whatever the value given here in the instruction. These two values will be added, and the result of the operation will be stored again in the W. Okay, so this is what the add LW instruction is going to do. All the 5 status flags will be affected based on the operation. Of course, all are, it doesn't mean that all of these flags will become 1 or anything like that. It's not like that. It is dependent on the operation that is happening, the result of operation. If the result of operation is 0, this 0 flag will be set. If the result of operation is above FF, carry flag will be set, and likewise. Okay. This instruction is 16-bit instruction. That's why it is called one word instruction. Now remember, whenever you are writing instructions, the number of words is also going to help you to identify whether you have written the instruction correctly or not. For example, I'll tell you. Okay, here the instruction is add LW 0x05. Okay, the instruction itself says that it is addition of L and W. Okay, so and you already know what I told you, that there are only 4 16-bit instructions. Which one? 16-bit instructions are go to, call, okay, then move FF, and LFSR. These are only 4 instructions which are 32-bit. Okay, rest of the instructions, whatever instruction comes your way, all those are 16-bit instructions. Okay, so you must understand that the instruction, whatever you are going to write, must fit inside 16 bits. Okay, remember what I'm telling you. Just remember, listen to this carefully. The instruction, whatever you are writing, must fit inside 16 bits. Okay, now if the instruction is let's say add LW. Okay, so here in the instruction, any instruction will have opcode, obviously, right? Because without opcode how can you know what instruction is it? So opcode is going to take up some amount of bits, right? Now, since there is a L, it has to be 8-bit for L, right? So 8 bits for L and some bits, let's say we don't remember how many bits, but some bits for opcode. So there cannot be any other operand, any other hexadecimal operand to this instruction. Can you, are you getting what I'm saying? Why I'm telling this is because many times people make mistake of writing two operands here. Let's say add LW 0x05 and 0x whatever 07. So this is obviously going to be wrong because we know that except these 4 instructions, all other instructions are 16-bit instructions. So we have only 16 bits to store the instruction. We have only 16 bits to store this instruction. 8 bits are going to be taken up by this value. Some bits are going to be taken up by opcode. So you cannot have any other hexadecimal value in the instruction, right? So this is also a way of keeping up the size of the instructions and keeping it correct. Okay. Now let's say before execution of this instruction, W is 0x10. And then if we run this instruction, what will happen? The value of W, which is 10 hexadecimal value, and the literal value 05 hexadecimal will be added, and the result of operation, which is 15 hexadecimal, will be stored in the W. Okay, clear? Here obviously there is no D or there is no A bit, right? Because A bit is used for access bank, right? From yesterday's, if you remember, the A bit, it was for access bank to know what is the location of F, but here is no F, so there is no question of access bank or BSR. Again, there is no question of destination because there is only one register involved in the instruction, W, right? There is only W register involved. L is not a register, L is just a value. So 5 is getting added to the value of W. So, and obviously the result has to be stored in a register. So it is destination will automatically will be W. Okay. So this is how the add LW instruction is going to work. Whenever a question is asked, explain the instruction, you have to write it in almost the same kind of format. Okay. Along with example. Okay. Along with example, you must write the syntax, the range of K is 8-bit in this case, so 0 to 55, 0 to 255. Operation you must write, you must describe the operation, you also must write the status affected, and you must give an example also. Okay. Now let's see another addition instruction which is called add WF. Now what it indicates? W is always what? W is working register and F is indication for the file register. Now as file register comes in, A also comes in. If there is F inside the instruction, there has to be a inside the instruction, because F in the instruction whenever is given, it is always given as 0 to 255 value, 0 to FF. Okay, and address of F is always 12-bit. I'm repeating it again and again, right? I'm repeating it again and again to see you show you from this value. Okay, whenever F is given, it is always given as value of 0 to FF or 0 to FF. Okay, so we need 12-bit. So for the upper MSBs, 4 MSBs, we can either have BSR or we can have it from the access bank. Okay, and in that case we must have specified A. If A is equal to 0, we are going to use access bank. If A is equal to 1, we are going to use BSR. Okay, so as there is F inside the instruction, there has to be a also inside the instruction. Okay. Now the operation is very similar. The instruction also will explain this. Add the contents of W with the contents of F. Okay. And where to store the result? It is decided by this D bit. We have seen yesterday the D bit, right? The destination bit. If D bit is equal to 0, destination will be W. If D bit is equal to 1, destination will be F. Means when the instruction is run, the contents of W are added to the contents of F. Remember, I am always talking about contents of W and contents of F. Many times mistakes happen that this F is also generally a 8-bit value. F is actually 8-bit address, but sometimes you may get confused by saying that and may confuse it with a value or data or literal, but it is F. It is a address. It is not to be taken as literal. Okay. It is to be taken as address and not as data. Okay. So after executing this instruction, the contents of W and contents of file register F are added together, and the result of the operation is stored in either W or F. If D is equal to 0, then the result will be stored in W. If D is equal to 1, the result will be stored in F. For example, if this is the instruction that I am running, add WF reg W, reg comma W. Now this is something interesting and something you may find different, that I am not writing D bit, I am writing directly W. But this is the facility provided by the PIC18F458 assembler that we use. Okay, instead of saying the W value of value of D as 0 or 1, you can also write here W directly. What it indicates that the result will be stored in W. Okay, result will be stored in working register. Okay, so let's say W in the beginning is 0x17 and register is 0xC2. Now remember, this 0xC2 is what? This is the value inside the register. Okay, value inside the register is W. Okay, so if it is the case, then the addition of these two will be done. 7 plus 2 is 9 and 1 plus C is D. So this is the result of addition, W, and after execution we will get W is equal to this value, and the register will contain the same value. It will not change. Okay. Instead, if here it was D is equal to 1, then this value D9 would have been stored in REG and W would have remained unchanged. Okay. So this is how this add WF instruction is going to work. There is a similar instruction add WFC. The only change is this carry bit is also added. While adding the contents of W and F, the carry bit is also added. Carry bit is what? Carry bit is the status bit. Carry, that status bit we have seen, the status register, that carry bit is also added here. Where will we use this kind of instruction? If we want to add, let's say 16-bit numbers, we will have to use this kind of instruction. Okay, rest of the things in this instruction are exactly same as add WF. Add WF and add WFC are very similar. Only difference is carry bit is also added in this instruction. Okay, so we will stop here, and I'll let you ask if you have any questions.